Thank you, Wing. Thanks for this invitation. So I'm going to try and give you a brief overview of the plasma environment of the moon, which is actually a lot to cover in 25 minutes. So I won't go very deep, but I'll try and cover some of the basics. First, I just want to kind of set the scale and say that there are a lot of different scale sizes involved in the plasma environment of the moon. The moon itself is a relatively big object in terms of plasma scales, and it interacts with the influences from the sun, such as solar wind and solar radiation. Because the solar wind is a supersonic flow, when it impacts the surface of the moon, it leaves a trailing void behind it, a wake region. And there's some very interesting plasma physics as that wake refills. At somewhat smaller scales, the moon actually has localized regions of magnetic field, magnetized patches on the crust, and those also have interesting interactions with the ambient plasma on somewhat smaller scales. And then at one of the things that happens with those magnetic anomalies is that part of the solar wind can reflect from them, and then those particles can follow complex orbits. Some of them can go into the wake. So I'll talk about all these things. At smaller scales, there's a plasma sheath around the surface because the plasma interacts directly with the surface. There's no substantial atmosphere on the moon, so nothing to stop the plasma from interacting directly with the surface. And then because of that interaction with the surface, there are electric fields created and particles can be reflected and emitted from the surface. And so I'll talk a little bit about those effects. And then finally, as you heard from our last speaker, the moon does not have an atmosphere, but it does have a weak collisionless exosphere. And that exosphere is both a source and a sink of charged particles. And so there are interactions between the exosphere and the plasma environment. And if I have time, I'll touch on those a little bit at the end. So let me start from the large scale, the wake, and I'll start from the perspective of simulation. So these are two cuts through the wake. You can see the moon here, and then the wake is this trailing void in the density. The solar wind flows from left to right and is absorbed on the day side and then leaves this long trailing wake. Because there's a void there, the magnetic field is compressed into that wake to balance the loss of pressure from the plasma. And so you can see an enhanced magnetic field in the wake. That magnetic field that fills in the wake has to come from somewhere. And you can see if you look in the plane perpendicular to the field, there's a rarefaction region where there's a reduced magnetic field. And you can also see that signature in the density. So this is a 3D simulation, but it's also consistent with what we see in the data. These are now a synthesis of many observations from the Artemis spacecraft around the moon, showing the same values as in the previous plot, unfortunately on different scales, but you can see the same features, a long trailing wake in the density, an enhanced magnetic field in the central wake, and these rarefaction regions where the magnetic field expands into the wake and then compresses in the void. So the magnetic field plays a very important role in the dynamics of the wake. You can see that in the plane parallel to the magnetic field and the plane perpendicular to the field, things look very different. The magnetic field plays a key role in determining the structure of the wake. The plasma largely expands along the magnetic field into the wake. And actually the ions are accelerated as they expand into the wake along the field lines. Because of the tilt of the magnetic field, that can result in either energy gain or loss in the solar wind. Meanwhile, if you look at a cross section of the wake, then there's also fluid forces that compress the magnetic field to maintain pressure balance. And you can see this is what causes this enhanced magnetic field in the center of the wake, and then these reduced fields around the edge. Now, all of this process as the plasma fills in the wake is very, very efficient at creating unstable plasma distributions. And so there are a lot of plasma instabilities that occur in and around the wake. Some of those are on ion scales. And this is a couple of sets of simulations showing instabilities on ion scales. What you're looking at here in the left here are cuts through the distribution function. And you see the solar wind outside of the wake. And then in the wake, you see the ions being accelerated into the void from the two sides. As you go further down the wake, you see that these two ion beams coming from the two sides of the wake actually cross. Now that is a very unstable situation, and it leads to the formation of streaming instabilities. And you can see these ion holes forming in phase space. What those correspond to in real space are big perturbations in the density. And you can see those perturbations in the density forming here in a cut through the wake. Similar things happen with the electrons as well. So the electrons, rather than being accelerated into the wake, are actually decelerated. So most of the electrons that come in from the two sides of the wake are reflected and turned around. However, the most energetic component of the electrons can actually go all the way through the wake. And if it makes it through the middle of the wake, then it actually can be accelerated out the other side. And what that does is it creates you electron distributions that have a peak in distribution function, like the distribution function shown down here in panel C, for instance. You can see there's this little peak here in the distribution function. Now, this is a cartoon, but we also see this in the observations. So this was actually one of the very first wake flybys that we did with the Artemis spacecraft when we first put one of these spacecraft in orbit around the moon. And what you're seeing here are two electron energy spectra, one for electrons going parallel to the magnetic field and one for electrons going anti-parallel. And you can see in the parallel distribution, there's this very intense beam of electrons. So these are electrons that have gone all the way through the middle of the wake and then been accelerated out the other side. And they create a beam instability, and that drives electrostatic waves, which you can see in this Fourier transform of the electric field spectrum here on the bottom. So the wake is just full of plasma instabilities at both ion and electron scales. If we move down in scales now from the size of the whole wake down to slightly smaller scales, then the next interesting thing to talk about is the magnetic fields of the moon. So many people, when they think of the moon, don't necessarily think of it as having any magnetic fields. And indeed, it does not have a strong global magnetic field like the Earth, but it does have small patches of magnetized crust, which we think were actually magnetized by a primordial dynamo that is no longer active. Those fields are very weak. You can see that the scale here is 10 nanotesla at 30 kilometers altitude. So you guys are sitting in a field of about 50,000 nanotesla right now. So compared to Earth fields, these are very, very weak. They're also very inhomogeneous. You can see that the polarity goes from red to green and red to green all over the place. So the fields are very inhomogeneous, pointing in different directions, very small scales. Just to talk a little bit about how very small the scales are, I want to compare the scales of these little lunar magnetic fields to some other scales that you might be more familiar with. So this is a simulation of the Earth's magnetosphere. You can see the size of the terrestrial bow shock here. This little circle here is not the Earth, but it's the inner boundary of the simulation, which is actually 6 times the diameter of the Earth. So the Earth's magnetosphere is a nice big thing. If we go down in scale a little bit, Mars's magnetosphere is very small compared to the Earth's magnetosphere. You can see that if you put Mars's magnetosphere, it's just a tiny little postage stamp compared to the size of the whole Earth's magnetosphere. The moon is still smaller yet. So the moon is about 3 times smaller than Mars. So here's the moon sitting next to Mars. If we blow that up, one of these little magnetic field regions is something like this. So compared to the size of the planetary magnetospheres that we're used to thinking about, these magnetic fields on the moon are just tiny. And they're so inhomogeneous that actually most of us didn't think they would be very efficient in doing anything to the solar wind. However, it turns out that they actually are very good at reflecting the solar wind. So this was the first map of ions reflected from the lunar surface, or really reflected from just above the lunar surface, reflected by these crustal magnetic fields. This map is made from data from the Chandrayaan mission. It's actually a Swedish instrument on an Indian spacecraft, which is kind of a cool international collaboration. What you're seeing here, the contours are actually outlining the strong crustal magnetic field regions on the moon. And the color scale is showing you the flux of solar wind ions that are reflected from them. And you can see that wherever there's a strong magnetic field, a set of contours, there are reflected ions. And it turns out that these reflected ion percentages can reach over 50% in some of these strong regions. So despite how small and inhomogeneous these magnetic fields are, they can actually reflect a lot of the solar wind. So this was actually quite a puzzle to us because these features are actually small compared to the solar wind gyro radius. So how can it possibly be that they can reflect the solar wind? Well, the answer is that the electrons do the work. So the ions have very large gyro radii, and they're barely magnetized in these fields. But the electrons, which have much smaller gyro radii, are still magnetized. And so the electrons get reflected. The ions try and just dive right into the magnetic field, but that sets up an electric field which helps reflect the ions and keeps the electrons and the ions tied together and keeps the plasma neutral. So we believe that there are strong electric fields in these magnetic anomaly regions that actually do most of the work of reflecting the solar wind. And this is a simulation over on the right that shows what this might look like. Now, this has interesting implications for the surface of the moon because in these strong magnetic field regions, we believe that most of the solar wind is reflected before it actually reaches the surface. And even the portion that doesn't reflect is decelerated by the electric fields in these structures. So this simulation on the top here shows the ion energy spectrum that you might have at the surface in one of these strong magnetic field regions. And you can see that the ions are strongly decelerated and actually almost completely excluded from some regions. What that does is it actually changes the weathering of the surface. The solar wind bombardment of the surface is actually one of the things that takes the dusty lunar regolith and darkens it over time. So as it turns out, these regions with strong magnetic fields have visible markings on the surface that look like this over on the right. They kind of look like the cream that you pour into your coffee before it fully mixes in, right? They're kind of swirl markings, a lot of people call them. What we think these represent is they represent regions that have been shielded from the weathering influence of the solar wind over time. So the plasma physics actually has an imprint on the surface of the moon. It also has more global effects because these ions that are reflected from these crustal magnetic fields continue to move after their reflection. If you look at what they do in the plasma frame, they follow circles around the magnetic field. But if you look in the frame of the moon, they follow these big looping trajectories, which are called cycloids. And the scale of these trajectories is quite large. It's comparable to the size of the moon. What this does is it allows these ions, which are reflected from small scale magnetic fields on the front of the moon, to actually gyrate around the moon, and some of them actually can dive right into the wake. And we see examples of that in the data. So this is an observation from the Japanese Kaguya mission, and it's showing a traverse of the lunar wake. So you can see the solar wind here, and then you go into the lunar wake where there's no solar wind, and then you come back out into the solar wind. But lo and behold, here in the middle of the wake, there's this sudden burst of ions. And these are actually ions that were reflected on the day side and gyrate into the lunar wake. When they do that, they introduce a bunch of positive charge right in the middle of the wake, and that pulls electrons along the magnetic fields into the wake. And this is another way that you can generate plasma instabilities in the wake. We also believe that these reflected ions may be responsible for creating a feature that was seen all the way back in the 1970s, and which has been called limb shocks or limb compressions. And the reason for that nomenclature you can see in these traces of magnetic field. These are consecutive orbits of one of the Apollo subsatellites going through the wake and then coming out of the wake. And just after the satellite comes out of the wake, you see this sharp increase in the magnetic field. And you see it on many, 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 many orbits consecutively. So the geometry of that orbit is shown over here on the right. The spacecraft is going through the wake, and then it's coming out, and it's seeing the strong compression of the magnetic field just after you come out of shadow, right near the lunar limb, which is why it's called a limb shock or a limb compression. According to simulations, it seems that these limb compressions may also be related to the protons which are reflected from magnetic fields. So this is a particle and cell simulation from Shahab Fatemi, and it's showing the magnetic field, the density, but the density has been split into two parts. It's got the solar wind density, and then it's got the density of these reflected protons. And you can see that it's just where these reflected protons maximize in density that you get a strong compression in both the density and the magnetic field. And we believe that this is due to the interaction of the solar wind with these reflected protons. So here's some kind of pictures that show what the trajectories look like and show that where we see these features, it's where there is momentum transfer between the reflected protons and the solar wind. So the orange and green arrows here represent the forces due to motional electric fields between the reflected ions and the solar wind. And so the orange arrows is the force on the solar wind. And you can see that here there's an orange arrow that's outward. So the solar wind is being deflected out and forming this compression. And here also this orange arrow is outward. The solar wind is being deflected outward and forming this strong compression here. So it's a really cool kind of process where there's a small scale feature that reflects the solar wind, but then those reflected particles follow these large trajectories that cause global perturbations to the system. So it's kind of a coupling between different plasma scales. Down at smaller scales, I mentioned that there is a plasma sheath near the surface. So that's a localized region on the scale of the Debye length where the plasma is non-neutral. On the day side, on the night side, I have the night side here first. That's an ion sheath. So in an ion sheath, what happens is that the electrons have faster thermal velocities. So the electron current to the surface charges it up negative, and you get a negative surface. It turns out that we can observe that from orbit because there are secondary electrons that are generated from that surface, and they get accelerated up and form a beam of electrons. And you can measure this beam of electrons, and it tells you the potential difference between the surface and the spacecraft. So this is expected and not surprising on the night side. On the day side, it's more complicated because there are also photoelectrons, but it turns out that in some situations, even on the day side, you can get this kind of a sheath where the surface is charged negative compared to the plasma. And again, you can get an electron beam coming up from the surface. So because of the presence of these electric fields near the surface and these non-neutral layers near the surface, you get emission of beams of electrons from the surface. So the takeaway from both of the last topics is that the moon emits plasma in all directions. In regions where there are strong magnetic fields, there's this reflected solar wind. And wherever there's one of these non-neutral plasma sheaths, which is basically all over the moon, there are electrons which are emitted. And so these electrons and ions generate all sorts of plasma instabilities around the moon. Indeed, if you look around the moon and you look for the presence of plasma waves, they're everywhere. So this was a study that Yuki Hirata did a few years ago. And he looked at where reflected ions are present. And you can see that within about a lunar radius on the day side, and then all over the place downstream from the moon, there are these non-solar wind ions. So these are reflected ions that have been reflected from magnetic fields and from the surface. And then if you look at plasma waves, you find that there are also plasma waves in all these regions. Low frequency plasma waves where you see the ions. If instead you look at high frequency waves, then you can see those anywhere that the magnetic field is connected to the surface, because the electrons that are emitted from the surface run along magnetic fields and they generate these instabilities. So it turns out that if you look at the right kind of features, namely plasma waves, you can actually see the moon coming from many, many lunar radii away. You'll notice that there are some dots here that are colored that are like 10 lunar radii away from the moon. So that's many, many thousands of kilometers. So the moon actually perturbs its environment quite significantly if you're looking at plasma features. Okay, the final topic is kind of to connect to Rosemary's talk. The plasma around the moon actually is both a source and a sink for the exosphere. So the first part here is that the plasma is a source of the exosphere. A lot of the volatiles on the moon can be delivered from the solar wind. So this is an example in the form of helium. What you're looking at here is actually a comparison between two completely different measurements. The black dots are measurements of neutral helium in the exosphere of the moon by the LADEE spacecraft. The red line is actually a calculation of the flux delivered of alpha particles, doubly ionized helium, from the solar wind. And you can see that there's a nearly perfect correlation between them, showing that most of the helium in the lunar exosphere is delivered from the solar wind. Here's just a scatter plot showing the kind of correlation that you get between these two. You'll notice it's not a perfectly linear correlation, and the intercept is not zero. And that's because there is a small endogenic source of helium from the interior of the moon. But most of it is delivered from the solar wind. So the solar wind is an exospheric source. The solar wind is also an exospheric sink, because if neutral particles from the exosphere get ionized, then they feel the magnetic and electric fields in the solar wind, and they become a pickup ion and they get carried away by the solar wind. So this has been observed by many different spacecraft. These are just a few examples here. The WIND spacecraft observed these at large distances from the moon. The Japanese spacecraft Kaguya has seen this. These are a couple different examples from Kaguya. And here's an example from LADEE, which I think is one of the best examples of this, because we had an instrument with very good mass resolution on LADEE. And you can see all the species of ions that are created from the lunar exosphere. Some things that you expect to see because they're delivered from the solar wind, like hydrogen and helium. Some things which are part of the regolith, like oxygen and some of the metallic elements. And some things were very surprising to us, like carbon and carbon monoxide. We did not necessarily expect to see these elements in the lunar exosphere, But it turns out that they can also be delivered by the solar wind. So the solar wind is a source of carbon, which we believe contributes to this carbon exosphere. There may also be some part of this carbon which is coming from lunar micrometeorites. But we can see all these byproducts as ions that are carried away in the solar wind. Even when you're not in the solar wind, there's material coming off of the exosphere. So this is an example now not in the solar wind, but in the Earth's magnetotail. The interesting thing that happens in the magnetotail is that in the tail lobe, there's almost no ambient plasma. So the ions that are ionized from the lunar exosphere actually become the dominant source of plasma. You can see these energy spectra here. There's basically no plasma. This is what background looks like in our sensor. And then suddenly you come near the moon and you see this burst of ions. When you see that burst of ions, if you look at what the velocity and the magnetic field are doing, you can see that the magnetic field actually gets bent because of these ions. And you can see kind of the geometry of that in these cartoons down here at the bottom. That local release of plasma from the moon actually perturbs the magnetic field in the magnetotail of the Earth. So again, the moon's presence can be seen if you can look at the plasma and look at the right things. Okay, so I think that's my last slide, and I think I'm out of time, so I'll happily take questions if anyone has any.
Hui Yang has a question for you, Jasper.
Okay. Yeah, first one is about the limb shock. How high of the limb shock?
Sorry, what about the limb shock?
Yeah, how high?
How high?
Altitude, yeah.
Yeah, so maybe I can go back to this figure. This of course is kind of a cartoon, but it does show one thing which is accurate, which is the altitude of the limb shock depends on what solar zenith angle you're at. So if you're close to the subsolar point, then you basically can't see any of these things at spacecraft altitude. They're all kind of under you. But if you come near the limb of the moon, then they can actually extend some distance from the surface. And we can see some signatures of the strongest varieties of these several hundred kilometers from the surface.
Okay.
Any other questions?
Yeah, actually, this Tiger speaking. Just wonder what will be the, is there any way we know the exosphere's height, or otherwise like exosphere pulse, what would be the altitude?
For the exosphere, there's not really one answer for that, because there are many different species in the lunar exosphere and they all behave very differently. Because the density is so low that it's basically collisionless, each species has its own scale height and its own characteristic behavior. So some of the heavier species like, argon and things like that are confined within a few tens of kilometers of the surface. But some of the lighter species can extend to great distances. The hydrogen and helium exospheres of the moon extend to many thousands of kilometers. Also, some of the metals that are particularly susceptible to radiation pressure, for instance, sodium, if you take an image of the moon's exosphere in sodium, you can actually see a tail that extends downstream many, many lunar radii. And so in that sense, the height of the sodium exosphere is almost infinite because it's escaping downstream.
Okay, I got an answer. Yeah, Jack, one more question. Could you show me the blow up this current slide?
Of the which?
This slide, current slide on the right over here. It's a microscope of the interactions. Yeah, blow up, please.
This one?
Yes. Okay, just wonder. You see, we will be able to see some, the few strands anomaly over there's a peak over there. What will be the location or the local time or what the moon time over here? Is it the dusk or the morning or what?
You can see these anywhere near the terminator plane. So if you're in the equator, then you can see them at both dawn and dusk. But you could also see them in the polar regions.
Okay, actually, I saw the one side is might be dawn, but the other one is dusk. So you mean whatever we show on the slide is dusk for both dawn and dusk?
It could happen around the moon, depending on the solar wind magnetic field.
Yeah, we'll see that, because in just wonder there's asymmetry between the dawn and dusk. That's what I'm saying.
Yeah, you can see these both on the dawn and dusk side. There's not really a strong preference for dawn versus dusk.
Okay, that's quite different from the ionosphere. Okay, whatever. Okay, thank you.
Yep.
How about the surface charging? The electrostatic charging of the lunar surface. Can you say a few words about it? I mean, that might be related to the space weather effect during solar storm, for instance.
Yeah. So typically the surface charge is negative on the night side, positive on the day side. So on the day side, the typical value is relatively small and positive. Few volts or something like that, and it's confined very close to the surface because the Debye length is a few meters. On the night side, though, because the plasma is much more tenuous and it's much hotter in the wake, the typical potential is larger, hundreds of volts and negative, and it's more extended because the Debye length is larger. So that's during typical conditions. Now, there are certain conditions where you can get much larger charging than that. One example is when you're in the Earth's terrestrial plasma sheet, because the plasma temperature is much hotter, then the surface charge gets much larger. The surface potentials get much larger, I should say. You can get surface potentials of kilovolts negative. Another example of a time when you can get large potentials is when there are space weather events. So when you get large energetic particle fluxes, particularly on the night side, you can get very large negative potentials. On Lunar Prospector, we inferred negative potentials of up to 4 kilovolts during a couple of very intense solar energetic particle events.
Would that have effect on the spacecraft, with such a large spacecraft charging effect?
As long as your spacecraft is well designed so that you don't have differential potentials across it, it's not really a problem for the spacecraft. You definitely want to make sure that your spacecraft is well conductively coupled so that you don't get big differential potentials. Because then you can get discharged. But as long as everything is conductively well coupled together, it's no problem. It's no different than going through the Earth shadow in the plasma sheet or something like that spacecraft around the Earth have done for decades.
Okay, very good. Any other questions from the other sides?
I have one more question.
Yeah, sure.
Yeah, I have a question about the magnetic anomaly. What does the size or the position of magnetic anomaly change with the surrounding condition?
You're asking, does the magnetic anomaly strength change with solar wind conditions?
Yeah.
No, the crustal magnetic fields are frozen into the rock, so the source of the magnetization doesn't change. If the solar wind field is strong, then it will compress that lunar field down towards the surface. So it certainly is perturbed by the solar wind, but the lunar magnetic field is it's frozen into the rocks, so it's a remnant field.
What happened to the helium? You talk about protons being refracted and so on. Do you see helium, alpha particles?
Yeah, so it doesn't seem like the alpha particles are reflected efficiently by these magnetic fields, and that's probably because they have much more momentum. So the electric field's just not really quite enough to reflect them.
And from what you said, because at the beginning, during the Kaguya time, Nishino, and the impression was that the lunar surface actually reflect the soaring ions. But from your description, most of them are produced by the magnetic anomalies, by the mini mesospheres.
Yeah, so the lunar surface can reflect a small percentage of the ions, but it's most of the ions that reflect from the lunar surface come off in neutral form. So most of the ions that reflect from that make it and hit the surface, if they reflect, they come off as neutrals. Whereas if they reflect from these magnetic fields, then they stay ions.
Okay, that's clear. That's very good. Yeah, I think that is very important to know. Okay, if there's no more questions, Esther, you have questions? You have no question. Sarah, you have questions? So in that case, thank you so much, Jasper. Well, this is a very, very nice lecture.
Thank you.
And I hope you have a nice evening still, right?
And a fine morning to all of you.
Yeah, I hope to see you soon in Taiwan.
Yes, I would love that.
Okay, thank you. Yeah, bye-bye.